We're looking at an idea called direct variation in this video. So direct variation is so the way two variables interact with each other is a very important idea as you move into higher levels of math. And so what we're going to look at first in this video is direct variation. Next video is going to be indirect variation. And so what we want to see is that when one variable is going up, the other variable is going up. They're directly connected to each other. And so if they're going up in that same degree, so if y is going up just as x is going up, there must be some constant that is making the relationship. So here's what I mean. So what we're saying is, on one side of this equation, we've got our balance beam here. Y is going up. Well, if y is going up, if this is going to stay balanced, x is also going up. And so they must be in some kind of ratio. There must be some constant, some number that if you divided them, you always got the same thing. So suppose y is 3 and x is 2. If this goes up to 4, this has to adjust as well. They have to stay in that same ratio. So the way I think of direct variation is this. You've got one of them varying directly on each side of the equation, and there must be some k that keeps them in that ratio. It doesn't mean y and x are the same number. It's just that they stay in that same ratio, and k is the value that keeps them in that ratio. Let's do some of these, and I think you'll understand. Okay, so here's what we've got. Y varies directly with x. Now, let's find that constant that's keeping them in the ratio. So what I'm doing here is this. Here's my equation. Y varies directly with x. So y is 20, x is 8. Now there's some number x. Now y and x don't equal each other. They just stay in this ratio. So we want to find what the value of that is that keeps them in this direct relationship. And so we're just going to divide the 8 over to the other side. Like I know it's 20 equals kx. We're used to seeing it like 8k. It's the same thing. Doesn't matter the order you multiply. So if we just divide the 8 over the other side, we have that value. That k, that constant that's keeping them in this direct variation, is 2.5. So we can make a generic equation. We say y equals 2.5x, and anytime x changes, y is going to change in this same ratio. So let's try another one here. They're telling us that y is varying directly with x. So I've got this again. Okay, so let's see what they told me. Now I want to find what is that value that keeps them in direct, that constant that keeps them in this ratio. That's k. There's some number that is keeping this in that same ratio. So I'm going to put a 3 in there for y. X is 10. Okay, now again, this is out of order. We're used to seeing this as 10 times k, but if we solve this, we get k is 3 over 10. Just divide 10 on both sides. So this is it. The relationship between y and x keeps staying in a direct relationship, and it stays that way as long as you multiply x by 3/10. It's always going to be the same. Okay, so we can do another one here. We've got y varying directly with x. So each of them has to be on one side of the teeter-totter. I've got 12 equals, I'm going to write it the other way around just because we're used to seeing it that way. So this is the relationship. There's some constant that always keeps this in equilibrium. Well, what is it? Well, we divide both sides by 4. So k is 3. Okay, so let's write the equation. I don't know if I did this on the last one. Let's write the equation. Any value of y and x have to have this relationship here, where this constant is 3. All right, now we're going to do some in the sense of word problems here. So calories is burns directly with the number of minutes. Doesn't that make sense? The longer you run on the treadmill, the more calories you would be expected to burn. So we're going to do the same thing. Now we've been saying it like this, y equals kx, but in this sense it's going to be calories are in direct relationship with the minutes on the elliptical or whatever the machine was, treadmill. Now they told us he burns 3:15, or she, whoever it was, in 18 minutes. So we want to find this constant. What is this rate here that is keeping this in equilibrium? we're just going to divide both sides by 18. And here's the constant. This is the relationship between them, 17.5. So we can then make the generic equation. Calories equals 17.5 m. So as they change here, this is what we get. It's actually the same idea as a slope. So as the minutes change by 1, the calories are going to go up by 17. The calories burned are 17.5. So it's got a lot of applications. For right now, what we're just seeing is what is that value that keeps this in equilibrium. Okay, so then they ask us to find, well, hey, what's C going to be? How many calories are you going to burn when you've done 25 minutes on the treadmill? Well, to find that, because we know they have this direct relationship, all we have to do is put 25 in for M, crunch it, and we get C is 437.5. They always maintain this relationship by this, well, I don't have it, C equals 17.5 M. Always keeps that direct relationship. Okay, this is going to be more of the same here, but let's do calories. Okay, calories is going to be in direct relationship with the time spent exercising. So here's my generic equation. We need to find K. So he burned 312 calories in 65. I'm going to put the K at the back there again. In 65 minutes. So, sorry, my calculator's not working. All right, so I'm just dividing both sides by 65, and K is going to be 4.8. So my equation is 4.8 times time. This is the relationship they always maintain. T and C are directly in relationship to each other all the time. Okay, what if he exercised for 90 minutes? So what we would just do to find part B is just put in a time of 90. So I get calories is not 432 calories. All right, same thing here. The book is great here. It's got a ton of examples. This gets a little repetitive sometimes, but we'll work them here. So distance is directly changing with time in this problem. So a train goes 100 miles in 2 hours. So to solve this, we would just divide both sides by 2. I'm going to get K is 50. So here's my real formula. This is how they're interacting with each other directly, and this constant of 50 is in there. Now, how far would we go in 5 miles? So let's just multiply that by 5. Our distance then, I'll just do distance, is 250 miles. Just multiplied that out. Okay. I should probably just let me run through this one quick. There's going to be more of the same. There's really nothing new about this one. There's going to be a variation at the end. But so, okay, so we've got gallons and miles have a direct relationship. So they tell us this information, and we can then solve for K just by dividing both sides by 469.8. And there is our constant, so we can then build our formula. Yeah, here it is. I was wondering where it was. Okay, there's our formula. Okay, exactly the same thing. Now we're plugging in 1,000 to find out how many gallons she would have burned. Same thing we've already done. So I'm going to skip these two because they're the same. But what we're going to get here at the end is, look at this one now. What they're going to say here, we're going to get a little bit more mature here in this. We're going to say that the load varies directly with the square of the cross section. So now instead, I don't know what variable, let me see what variables are going to use. Okay, L is going to be load. So there's some constant, and C is the cross section, but it's not varying directly like this. It's with the square of the cross section. So it's C squared. So they're in, it's not saying L and C are in this direct relationship. It's saying L and C squared are in this direct relationship. So just a little twist here. So L and C squared are now in this direct relationship. But other than that, we are going to work it just like we did before. So here's our direct relationship is now L and C squared. Plug in a value for L, plug in a value for C. Now it's a little more complicated. Remember, exponents have to be done first. Divide and there's our constant. So now that we have that constant, here's our equation. We've replaced k with what it actually is when we solved it. And then I'm sure they're asking us to do a particular application. They're saying what happens when c is 8? Well, we just drop it in the equation like we did before, and we find the maximum load is 300. Okay, so once again we're here, object. Okay, so we've got distance is varying directly with the square of the time as it falls. So it's not directly with time. It's not distance in time. It's distance in the square of the time. So we need to find k here, and they've given us what we need to find it. We've got a time, we've got a distance. So I've got 144 equals k times 3 squared. So 144 equals 9k. We're going to divide 144 by 9 to find that value, that constant that they're in that relationship with, and it's 16. So my formula is d equals 16 t squared. I now have found that constant for that direct variation. Now all we need to do is find the second part here. How far will the object fall in 4 seconds? Well, 16 times 4 squared. So that's going to be 16 times 16. So I'm just crunching it. You would do the exponent first, but that's going to be 16 again. So I get 256. Okay, we should put some units on there. Feet. Okay, so I think we have, yeah, just one more of these. Let's do one more. Pause it if you want to try it on your own here. So we've got area is varying directly with the square of the radius. So here's what we got. Okay, but now we need to find that constant. So we've got an area of 113.04 k radius squared. So just like before, we're doing the same thing. Dividing that by 36. So k equals 3. Sorry, that's supposed to be a 3. 3.14. So I have my equation. Sorry. There's my equation. All right, it's all set up. Now, what about the area of a pizza with a radius of 9? Well, just have to crunch this. So we times that by 9 squared is going to be 81. So my area is going to be 254.34. And that would be square inches. Okay, so that's direct variation. These relationships are on opposite sides of the equation. They keep changing in the same ratio. And we need to find that ratio, which is that constant k. And that should take you through that. We're going to move on to indirect variation in the next video.